Hello everyone, welcome to today's session. I am Ramesh, working as an assistant professor in the Department of Aerospace Engineering. In today's session, we are going to discuss about the stress strain diagram for the mild steel. What is stress? Already we have discussed in the previous class. Stress is the resistance force offered by the body to meet with the load, and with the empirical relation of stress is equal to force by unit area with a unit of Newton per meter square, and strain is defined as the change in length to the original length or change in the dimension to the original dimension consideration. That is a linear strain and a lateral strain. There is no unit for strain at all. But in this stress strain diagram, we are having a graphical representation. Strain diagram is a graphical representation of how mild steel deforms under increasing the tensile load. So we can have a stress in the y-axis, strain in the x-axis. It shows the relationship between the stress, that is force per unit area, and strain, that is deformation per unit length. The diagram reveals key mechanical properties of mild steel, such as the elastic limit, yield strength, ultimate tensile strength, and fracture points. These are all the important things. The key points on the stress strain curve for mild steel are elastic region, that is elastic limit, proportionality limit, then elastic limit, upper yield point, lower yield point, that is strain hardening region, then ultimate point, finally the fracture point. Here in the stress strain diagram, we have a point OA, where up to point A, that is called a limit of proportionality, where stress and strain are directly proportional to strain. So, and the material behaves elastically. That meaning it returns to original shape when the load is removed. This region follows the Hooke's law. That's why the OA is a straight line. It is not a curved or non-linear line. So that the stress is directly proportional to strain. If stress is increased twice, the strain also increased 2 times. Like that, it can go as well as a linear law. So that Hooke's law exists up to the elastic limit. The point A is called the proportionality limit, and we have another point A to B. The B point is called elastic limit. So beyond the limit of proportionality, the material still deforms, especially up to the point B. However, the relationship between the stress and the strain is no longer linear. Okay. Next, we can have another point, C and D. Put together, we can have the point as yield point. The point C as the upper yield point, D is the lower yield point. So at point C, the material starts to deform plastically. This means the deformation becomes permanent. So when you are applying the load, then deformation occurs. But if you release the load or unloading, if you're doing that, it does not regain its original shape. So plastic deformation means permanent deformation. So physically, it becomes the plastic region. So the deformation becomes permanent and the material will not return to original shape when the load is removed. Point D is called a lower yield point. That means it represents the minimum stress required to maintain the plastic deformation. So lower yield point represents the minimum stress required to maintain the plastic deformation. Then the region called D to E, that is DE, that is called strain hardening region. Strain hardening region. That is after yielding, the material requires an increase in stress to cause further plastic deformation. After yielding, the material requires an increase in stress to cause further plastic deformation. This is because the material becomes stronger due to the internal structural changes. So this region is called a strain hardening. So due to the strain hardening, the material becomes stronger due to the internal structural changes. Then the point you just look at that. That is the maximum point along Y side. That is the maximum stress the material can withstand before it starts to nick in the localized reduction in the cross-sectional area. So what is necking? Necking means you just see our body itself. You have a head in between throat you are having, and then we can have a body up to stomach. You can consider here. So between head and this one, we have a neck. This is called necking. You just see the shape here itself or dimension. The dimension point of view, there is a reduction in the area. Okay, or diameter wise, it is the diameter will be reduced here. So reduction in the area, cross-sectional area, what happened in the stress, we should know. So as we know that stress is equal to force per cross-sectional area. So area is in the denominator. When you apply the value less value here, okay, because of the reduction in the throat, that is necking, okay, in the neck, what happens? The stress will be higher. Okay, so the point E represents the maximum stress the material can withstand before it starts to neck. That is the localized reduction in the cross-section area is given. Finally, we have another point F here. The F is nothing but the material finally breaks or fractures happen. So after attaining this maximum beyond the ultimate point, the material goes to rupture. Because of the necking happens, after necking what happens, further you are increasing the load or stress value, immediately it will break. That is, fracture happens. So this is done in the UTM, Universal Testing Machine. That means the tensile stress is applied on a material. Initially, it is a rectangular rod, measure the dimension and the length. So top and bottom surface can be fixed. Then you can apply the load. What happens? The proportional limit attains. Then it attains the elastic point. Then yield point attained. Where yield point attained, there will be a deformation without increasing the strain, that is increasing the stress value, that is called the yield point. Okay, after that it attains the maximum ultimate point where the stress level is very high. After that what happens? The necking will happen, there will be a change in reduction finally. So in between midpoint you will have a change in diameter. Finally, further increasing, it will break immediately because of the stress level is higher in the necking area. So in simple terms, so imagine stretching in a rubber band. Initially, it stretches easily and returns to its original shape when released. A elastic region, that is called. If you stretch it too far, what happens? It may not return to its original shape. That is called plastic region. Okay. The stress strain curve for mild steel shows how it behaves under similar stretching forces, highlighting its strength and ability to deform before breaking. So this is about the stress strain diagram. So once again, I will tell you the important point: stress strain diagram. It is the graphical presentation for how mild steel deforms under increasing the tensile load. In the graph, we are having the stress in the y-axis and the strain in the x-axis. So we are going to increase the load so that the stress will be increasing. So how it will deform? From the proportionality limit is the first point it occurs, first stage. Then it attains the elastic limit. Up to this, the Hooke's law is valid. Beyond that elastic limit, Hooke's law will not be valid, will not be exist because stress is directly proportional to strain. So there will not be linear line beyond the elastic point. It will be a non-linear one. We can see that one from after the elastic limit, you will have a yield point where we can have the deformation with no increase of stress value. Okay, then we have a strain hardening. Here, strain hardening, we are having that material requires an increase in stress to cause the further plastic deformation. So here, term elastic region, after that only plastic region will come. In plastic region, we can remove the load, but the material does not regain it to its original shape. Then we can have an ultimate tensile strength point, that is the maximum stress that material can withstand. Beyond that, it goes towards the fracture. In between, we are having another reduction in material called necking. So further increasing the stress, you have a fracture in the material. So this is about the stress strain diagram for the mild strain, but depends on the material, type of material, it will, the stress diagram will change. For brittle material, this kind of elasticity, everything is not there. Directly, it will go under fracture. Example, glass. If force is applied, immediately it will be broken. Like that, each and every type of property of the material, the stress strain diagram will vary. So that's all in today's class. We will see a different topic in the next class. Thank you all.